worse, just a theory of anything.
All right. No, that's in there. Yeah, I'll have to get that. I do have some Ponder Stibbons quotes in there. And it was about, it was that that looks very, whatever it is, that graphical thing is an excellent, very intuitive summary or something that helps with intuition, whatever it is, helps with intuition greatly, but is wrong in every detail. The other great line is, that letters and a few letters and some rules of grammar don't make a story, right? It's a perfect complexity story. Yeah, 26 letters and a couple of rules. So you have to get narrativium, right? The sixth element. The fifth element is surprise. Okay, so it's pretty bad. All right, team, I'm sorry. Those things are on, and then this thing has to be... Do I turn it on? Oh, yeah. Okay, I turn it on. Okay, good. Right. Come on, thing. Math time. Sorry. Okay, so we're going to do some more of the spreading business. We will do random bipartite networks. Very beautiful. I mean, it doesn't have to be about spreading, a little bit of spreading, but that is just a big story. There's a great work by Newman and Watts and Strogatz from 2001, actually, so it's early on in this whole business. It's a great paper. It gets at all these things. So we'll dig into that one. I have to build the slides for that. And then we'll get to structure detection, which is awesome. And we may have organizations, might be a piece I'll put in there at the end, depends how we go. And chaotic contagion, I might even talk about that madness, which is pretty awesome. Okay, so, all right. So, contagion. So we've talked about spreading and it was hard, right? So generalized spreading processes, ungeneralized what we call generalized random networks, which meant arbitrary degree distributions, which is not, entirely fully general, obviously, right? But yeah. So we're going to go to generalized. Oh, right. Okay. So we're going to have this same story. Somehow in our contagion mechanism, we're going to figure out what's the probability that if one of your neighbors is on and you have K friends, what's the probability you switch on? So we know that there's a simple story. If it's biological contagion, it's independent, doesn't matter what other people have done. But if it's more of a social type one, we care about what our other friends are doing. Okay, so we want to find the largest component, basic thing. How bad is it going to be? And of course, we want to find finding giant component. Okay, so finding giant component, that's absent the disease spreading thing. That's just finding giant components. And then we want to start spreading some things on it and see what happens, right? May or may not reach the giant component at all, but we need to do that. So this is structural. This is a little dynamics on top of that structure. And then we'll look at some of these probability stories for probability of spreading. Okay. Yeah, all right. So this is a way of saying, right, generalized contagion. Okay, fair enough. Fine. All right, so generating functions. Yes. As requested. I mean, I wasn't going to put them in. Kidding. I'll show you a couple of different approaches, and you'll see there are, some are horrible. I recompiled things. We'll see if it works out. All right, so we have, now we have to worry about which node we're at, right? Because they're going to be correlated with other nodes. So we have to think about the properties of the nodes we're at now. We have to put that into our equations. Before it didn't matter. Edges just randomly connected to some other node. Didn't matter. So now we're going to have to work, because it's all, okay, so we talked about assortativity of all sorts of properties. This is only just about degree. So we're sticking with that. So we have a degree j plus 1 node. We're worried about what's the probability that, or we're thinking about what's the probability that it leads, the thing we want to capture is the probability that it leads to a subgroup. So for contagion, it has to be, this is an infected subgroup. For just the giant component, it just has to be the structural subgroup or subcomponent of size n, right? So we're going to have these two pieces. So before it was just this would have been row n, for example. right? We had row n. Row was the probability that if you go out on a link, you get to n nodes in the subcomponent. Now we're calling it f, and it's going to be n comma j, right? So we've got the size of that subcomponent is n, and we're coming from a node that has actually j plus 1 friends. So we've always got this little bit of I plus 1, j plus 1 trickiness. Okay. Yes. So we have this probability of infection. So that gives us a vector, right? So we're going to turn it again into linear algebra. Total excitement. And some sneaky calculations, actually. So, all right. So we're going to find an infinite set of generating functions. Why not? Right? One is fun, so why not have more? And it'll be for each node type here. And so types again are the degree. Degree here is j plus 1. So this is a degree j plus 1 node that we're thinking about. And what's the generating function for the? So these are probabilities that its edge leads out to n nodes in a subcomponent. Okay? So we're going to hang those probabilities on these x to the n's. All right. So it's very similar to what we've done before. So we have to look through it. It's a recursive relationship again. Right? It's that same idea. It's random. We just need to go one step to get a recursion story. So our generating function can be written in terms of itself in the following way. And this is about this problem. Well, you remember this picture? We had this guy here, pi of n, and then we expanded this out, and we thought about, right, and it has k friends in here, k friends. So this is, we added pk is the other piece here, right? The probability that you have k friends. We're interested in what's the probability that you are part of a group of size n. So all of these had to add n minus 1. Plus 1. And so it gave, so that this is a local piece of information and it connects these two global pieces, right? So we can expand this out one step. That probability that we are part of a group of size n has to be the probability, sum over all these probabilities that we have k friends and that our k friends are parts of subcomponents that add up to n minus 1. All right, and we had the row n one as well. Row n, and that actually used r of k. Right, so that's our local. So k other friends, and so we get this expansion as part of these blobs, little lollipops. Okay. Yeah, there's a node in here. So we're going to try this. We understood this is the one to solve, and then we can feed it back in here. So we're going to solve this problem here for this very general thing. Now we care about the flavor of this guy. Right, so this is, instead of row n, is becoming fnk. Is that what I called it? That's what I call it. Yep. All right. Okay. So let's see how these pieces work. So this little blob here is the probability. So again, ejk is where you come from a node of degree j plus 1 to one of degree k plus 1. We're dividing by the probability that we came from a degree j plus 1 node. That's this piece. So this is this connection probability to a degree k plus 1 node. This is probably that we infect that character, right? So, and then they have k other friends, right? And so we get this product of generating functions because this was in your assignment just now. If you sum probabilities or you sum random variables, then you multiply their generating functions together, right? So this is saying we want to sum k random variables together. They're all the same, right? They're all about nodes that a k plus 1 degree node. What's it connect to? So we multiply the generating functions together. That gives us the generating function for the probability that the sum of these k random variables is n, or whatever you want that variable is. We get an x out the front. That's a sneaky trick number 2, which is just to say the first character counts as well. Plus 1, that's a plus 1. And then we have to do a little cleanup at the start. And I have the words here. We have a little cleanup at the start. So the x is 0. So this is the probability that we get 0. That means we go out on our edge, and this is the probability that no one get that one, we're going to reach a node, but this is has to be the probability we don't infect them. All right, so this is the probability that they have k+1 friends, and this is the probability that they don't get infected. So it stops. So this bit means that on our, right, we have this something times x, something, a constant, plus something times x, plus something times x squared, plus something times x to the 17. The thing times x to the 17 is the probability that our edge coming out from a node that has j+1 friends hits an infected subcomponent of size 17, right? The probability that it hits a subcomponent of size 0 means that this guy didn't go through. Yeah. I know it's total madness. I know. So in words that have come out, the words are here. So we have a recursion relation. You can find the expected size of these blobs, right? So what's the average size? I'm going to go out here on a degree. I'm going to set a degree j +1 node, run out on an edge. I'm infected. This edge is infected. What's the expected size of this infection? Again, it's this tricky thing where we talk only about the finite subnetworks. And then we dance around the whole thing and we end up with a 1 minus to get the giant component. All right, so we can do this. Everything's here. These are all fixed by the network, We're interested in these ridiculous functions. So fj in principle is, right, so it's fk to the k. Right, so these things are, non-linear looking things. But so there will be a problem when we try to solve some more complicated things, but actually we can find the average size. We can think about what the average size will be, and we're interested in when that explodes, right? That's going to be our critical point. That's when we know that contagion is possible. So we're going to struggle with this. We're already struggling. We'll get back to the Gleason approach. It's beautiful. Okay, so we're going to go through some torture, and hopefully you'll feel this other stuff which is nasty. Looks better. Okay, so we want to differentiate this, a generating function. We differentiate it, set x equals 1. That gives us the average size of whatever the thing is we're measuring, right? So that gives us the average size of this infected component. That's a property of these generating functions. We're going to use this property, which is that the sum, we're going to say that we're on the side of this thing where there are only finite components. There isn't a giant component. So we're on the side of this critical point where there's just everything's finite, right? It hasn't exploded. So we're going to sneak up to it from that side, and we're going to say that this has to sum to 1. So it's just simply the sum of the probabilities. Right? That's standard normalization, which we know fails once we get on the other side of the transition. But we can do it on one side. All right, so you take your derivative, and I've left some things out. So there was this to the power of, k, right? So you get one derivative, and you get this blob to the k minus 1, but it's equal to, we set it equal to 1, right? So the nasty piece in here, which the nonlinear piece, evaporates. Right? We're on the side of this phase transition. We're on this side, right? Big thing spreading. We're just in here. We're sneaking up on the explosion from this side. Not very good arrow. Okay. All right, so derivatives. Loving the derivatives. Differentiate this thing. We get a k minus 1, all of this blob, and we get the derivative of the blob inside. Set x equal to 1. This is 1 to the power of k minus 1. Is what? And we're just left with the derivative. So we have it there, and we had a simpler piece out here. We have the derivative out here. Let me think about this last part here. Where did RJ come from? Oh, yeah, right. So it's here. We're going to bring it back over on this side. Yeah. Yep. Right. Right. And there was a first term. Okay, so there's a product here. Did leave out some steps. So product here. Yes? There's a product here. So we differentiate this, right? We just get a 1. And so we have this blob. We set that equal 1. So this is just 1. And then we're summing over something that's nice. So we'll see that on the next slide. And if we leave this guy and differentiate this, that x will disappear, right? Because it's just x equals 1. So that's why we get this first term. That's from the product rule. We get this blob here, and we pulled an RJ over on this side. So now it's a linear equation, right? It's infinite. It's okay. It doesn't have to be. I mean, there may be J's and K's. There's some limit to what they are, but in principle, it's large. Okay, we should be able to rearrange this. We have, F7 depends on the F's from, right? It's delicious. It's totally delicious. Okay, so let's rearrange things and do some sneaky things. So we want to put this. We're going to put this sum over on this side. So this sum should be still here. Let's see. All right. This blob came back over to here. Just hanging around. This is just some number depending on the network. This thing we're going to put on that side. So that's all over this. So there'll be a k, ej, k. That's this part. The probability of infection is there. And then this derivative is sitting here. And we don't have a sum here, but we can do something elegant, which is to say, well, let's put a sum jk in here, and we'll put a delta jk there, a Kronecker delta. Just jam it in. Right? So even this thing, so 1 when j is equal to k. So it's the identity matrix, actually. We love the identity. So this is good, right? So there it is, really good. So you have, this is right? So it's a function of jk, and summing over k equals 0 to infinity. So this is a matrix operation, right? Matrix times a vector equals some vector. This is a function of j here. You sum the k out. This is something, right? There's a j index here. You sum the k out here, and you get a j index here. But it's this matrix times this thing. So we can solve it by, what do we call dividing in linear algebra?
We don't want to find the inverse, right?
Right. That was good. So yeah, so it is the inverse, but we don't want to do it because Danforth told you not to.
You said if you remember nothing else.
Yeah.
It's that increasing the evaluation points does not increase accuracy.
Some other things you should remember as well as that, but yeah.
Don't solve.
I realized it was context dependent. Okay, yeah, never do that. Okay. So, but it looks fun. You can write it down. So we can summarize everything we have here. Really is it's a matrix times this thing we're interested equals some vector, and in fact we can write it as a matrix times the vector here, right? The connection matrix probability, right? That's really what it was, right? It's the EJKs, so it's the E matrix times the infection probability matrix. So we can leave it like that. Everything's just laid out here, what the pieces are. This guy depends on the structure of the network, the probability of infection. So yes, we can undo that. So you shouldn't do it, right? So in principle, at least. But this is a bad thing to do. But at least gives us the idea that when this thing's determinant is 0, this is when we get explodorama, right? So that's when we hit this point. So, we get some idea. I mean, it's not necessarily physically intuitive. That's always a bit of a battle with these things. Average component size explodes at the transition. That's good. Yep. Is therefore this, right? So that would be the mathematical condition. But you'll be naughty if you try to figure this out. You can do it for very simple matrices, simple kinds of things. Okay, so this is, we'll find a much better condition, actually. So that's a horrible result, actually, right? It's not intuitive. It's some matrix. It's got some things in it. It's not obvious. And in fact, we had this nice result for uncorrelated networks. So I have it on the next slide. We'll see. See if I can sort of quickly talk about it. But if we go to an uncorrelated version, which we've studied well, then we know we have this nice result for that, right? So that was, it's in a different format. But if we go back to it's k minus 1 pk, right, divided by the average of k, this thing is greater than 1, right? And we have a bk1 here. So we'll call this, and as we go through, we'll get a better and better story for this. This is R. It's our gain ratio, I'm going to call it. What's the gain ratio in the system? So that guy should pop out if we put it into here. So if we put that into here, it should pop out. It actually turns out to be a tricky little bit of linear algebra, but very enjoyable. So these are just statements. If B1 is just a constant times the 1 vector, right, then it's just a simple disease model, which was, we suggested we could have this at the start. And if it's just 1, everyone gets infected, yay, right? It just spreads. You can imagine your disease spreads for free. Then that's the same as structurally finding the giant component. So this would be the condition for a giant component existing. So it's a nasty thing, and we'll want to find a better one, and we will. Okay. I don't want this to talk. Okay, so this is something I scribbled. You can't really see this very well. Okay. Let me just quickly say the words. That's this condition we had. We set this EJ minus 1, K minus 1 to RJ, RK. You can look at it later on. I know I'm interrupting myself. Get out of the way. Get out. Okay. So it's there's some really nice stuff in here. So for instance, there's an RK minus 1 factors, right? There was an RK minus 1 there, and there's an RK minus 1 there. So it factors out. Yeah, it's kind of a failed experiment. So what happens if you have a determinant, and then so it's really a matrix times a vector. That's not true. It's a matrix, and each column has its own thing that's multiplying, right? That's being multiplied by, right? So the RKs are these RK minus 1s are overlaying. So what happens if you have a matrix and you take the determinant and you have a factor for each? You want to pull a factor out of each column. It's multilinear, right? So each factor comes out, right? So if you take a 2 out of an n by n matrix, you get a 2 to the n. Yes, you remember. No, you don't. You get you get a product of all of the factors. Yeah. If you pull out one row's factor, it goes in front. If you pull out another one, so yeah. Because determinants are volumes of parallelepipeds in n dimensions. If you go to hospital now. I'm okay. So you can pull that out. That's a little factor that's there. I'm sorry about the resolution, but you can pull that out. So now you're left with delta JK minus this thing here, minus K minus 1, BK1, RJ minus 1. So there's a thing that's just got K in it and a thing that's just got J in it. So what sort of matrix is that? So this is the identity matrix. Right, we've got delta JK, I'll write it down, minus K minus 1, and it's a BK1, RJ minus 1, right? So we're trying to find the determinant of this thing. One way to find the determinant is to find the eigenvalues, multiply them all together. So that's what we'll do. The eigenvalues of a matrix where, so let's say we've got this matrix and we add the identity to it. What do we do to so we know these eigenvalues, what do we do if we add an identity to it? What happens to the eigenvalues? Not quite. So if you have A plus 7 times the identity, you've got the so this one has, let's say it has lambda 1 as its first eigenvalue. What's the first eigenvalue of this if we order them in the plus 7, right? And you have the same eigenvectors because it's identity, it's good. Right? This guy times V1 gives you lambda 1 times V1 plus 7 times V1. Okay? So we're going to get a plus 1 for that guy. So we need to know what the eigenvalues of this thing is. It's this actually. It's a matrix that looks like this. It's an outer product. That's what this maniac is trying to tell you. It's a outer product. Outer products are very special. They're rank 1. They're rank 1. So if this is vector A, this is vector B, you can see what their eigenvector has to be, because if you multiply this guy by A, you get B transpose A, just a number, times A, right? So this is the eigenvector, eigenvalue, and this is the eigenvector. So the eigenvector is always sitting there in a rank 1 matrix. It's just this first guy. So that's our, so this is our, actually this needs to go here. This is our eigen vector, and we just multiply it by itself, and we get the eigenvalue. Let me just say it. So the eigenvalue in this case is R k minus 1, k minus 1, b k minus 1. K equals 1 to infinity. That's lambda 1. It was minus sign, so we have minus that. And we're going to add 1. And we have that. And all of the others are 0. All the other eigenvalues are 0. And we add 1 to them, so we get 1 to the power of infinity. So we have this is our determinant. And this equals 0 when we have the condition that we had before, right? This is exactly the condition we had before. It's written in a slightly different way. This is pk over k for uncorrelated networks. So it's kind of disgusting, but you can get there. All right, I'm sorry. You want to complain? Rank 1. So yes, there's a whole story here, right? So rank is, so let's think of let's just say square matrices. If you do row operations, it's the number of independent rows. Let's say that. Let's just say that. So it only has one row in it. Because if you multiply this guy out, it's actually just all copies of B with different weights, or all copies of A with different weights. So it's the same thing repeated over and over. Linear algebra is fantastic. But this is akin to saying, if you think of it from the column vectors, the column space view, all your musical instruments sound exactly the same. They've just been dialed up and down. So to represent this sound, you just need 1. Super cool. Okay, a little madness in there, but it's there. All right, so okay. It does collapse back, but it's a lot. It was non-trivial to do that, but we forged a way through the forest of insanity to get there. Matrices of unusual size. Okay. All right. So we'd like to find triggering probabilities and, of course, the extent that the thing reaches. Okay, that's not in what we've done at all. We've just found a horrible condition. We were able to get back to the one that we can get from a physical point of view, but we have this terrible determinant story. Okay, so triggering probability, another joyous generating function situation. But basically, it's actually fairly simple to write this one. The vulnerable one is a little more complicated. You remember that whole vulnerable story? But this is, what's the extent that I get if I have k contacts and I'm switched on at the start? So I'm just switched on exogenously. I have k contacts. So I'm adding up these k samples. If you add up samples, you get products in generating function space. So we do this. We sum up over the probability of k for each initial, each value, each number of friends I could have. And then we get 1 for me as well, plus 1 for me. So that's just built in. So this gives you the, what's that? No, it's just, no, yeah, it's just another generating function. Just a different label. Sorry. Yeah, I know. Yeah, so that's for the component size from a triggering thing. So you can, so in principle, right? That this guy, if you can figure this out, this horrible beast, it's got the probability that you are part of a component of size 17, part of a component of size 18. That you're switching on induces a spread of size 18, plus 1, 17. It's all in there. And we didn't solve for this, right? That was hard. We didn't actually solve for that. We did have, okay, so yes, right. So this is one of these sneaky things where we find the we sum up the probabilities of reaching all the finite subcomponent, finite components, finite spreadings that we can envisage. If that's less than 1 minus that will be the probability that we're actually part of, that we induce a giant component spread. So we need to know what this horrible beast is in here. It's no longer equal to 1, right? We were sneaking around on the left-hand side before. We were saying it's equal to 1. We're sneaking around. Now we're over here. We don't know what it is. So we have to compute that thing, and it's bad. We go back to that original equation that we had that we differentiated. Here is everything again. Fj is in terms, that generating function is in terms of itself. We do set x equal to 1, right? So it is a, here's a vector, and here's that vector sitting in here, but it's a nonlinear equation. So we can't even do our horrible thing and find a, inverse, which we shouldn't do anyway. Anyway, so nasty, but we should be able to, do some sort of iterative thing. Okay, so this is sort of as far as this method goes. Let's do it in a cool way. So this is a better way. All right. Okay. So this connects to the Gleason approach for understanding the spreading on what was the Watts model, but is much more general. Let's try it in this way. So we want to see if we can get the final size. We'll actually get the whole thing, right? We'll get the size at time t, the whole business. Pretty spectacular. And we'll get the cascade condition, and then the next set of the next set of slides, we'll actually get these cascade conditions out in a much better way, right? So there's this sort of thing where we're looking for the largest size, and we're saying, okay, well, we know it explodes at this point, so that's going to give us a condition. That condition is a mathematical condition. We can get it. It's some adjacent, some matrices. The determinant of a matrix equals 0. Fine, but that's a nasty, messy little thing. We can actually get to it from a physical argument, and it'll be much more clear. All right. Okay. All right. So the extension, before we just had theta of t for this model, right? We said, what's the probability that an edge is infected at time t? Right, we're just somewhere in the network. What's probably that edge is coming from a node that's become infected. So now we have to think about where it came from and where it's going to. So if we're at a degree j node, the probability that an edge coming into that node depends now on j, because it's a sort of there are correlations. Right? Edges have flavor to them. Okay, so if you look back on the notes, it's not a big complication with that. I'll give you a little problem to work on with this. So the probability that an edge connecting into a degree j node is infected at time t plus 1 depends on, in principle, on all of these edge infections, right? The probability that an edge leading into a degree node of a node of degree 1 is infected, node of degree 2 is infected, blah, blah. So that's a whole vector in there. We had this story that it's either, well, its friend could have been infected at the time 0. That's your seed size at time 0. We are moving out to having a seed, right? This is the transition from the previous one, where it was a very specific node. Now we have a seed that's distributed. Okay, so with the probability, okay, so probably that your friend was infected straight away, exogenously. If they weren't, then we have this horrible looking beast, right? So this gives you your connectivity story here, right? So what's probably your degree J node? You're connected to a node of degree K minus 1. So before we didn't have this, we had a simpler thing. It didn't matter what our degree was. Probably if connecting to someone, as we've said a lot, depends on their degree, right? So your friends are strange. They have more friends than you. So but this blob is the connective piece. And then we have this stuff that we had before, but now all our thetas have K's in them, right? So let me get that right. Yeah, so so now you're connecting to someone who has K friends total. So the indices are in trouble. K friends total. And so there are K minus 1 other friends there. This is the probability that an edge coming into that guy at time t is infected. So you could have I of them on, and then you'd have to have all the rest off. And then this is the probability that a node of degree K is infected if I of its friends are on. Okay. So if we get back to just the uncorrelated one, these things disappear. Okay. Gonna get right. Okay, so again, edge to edge transitions. That's the story for these things. This is then at each point we can say, okay, I know what the fraction of edges are that are infected for any degree node, the incoming edges, and I can compute the overall fraction that are infected. So it's the fraction that were infected initially. If they weren't infected, then it depends on who their friends are, right? So if they have K friends, then the infections coming into them depend again on that K, right? So now the infections for edges depends on where they're going to, right? Before it didn't matter. So this is all computable. But the thing with this, it does prescribe an evolution. You stick in 5, 0, let it run. We have, and you guys have this in your assignments, we have then you have maps of the interval. Very nice stuff, right? What happens in the long-term limit. Okay, so it's this kind of thing. Now it's not, before it was, theta of t to theta of t plus 1. Now it's a whole vector to a vector, right? So nasty. Okay. We do a little, right? We're not just expanding a simple map anymore. We have to expand this G vector around this point, which is, it's 0, it's the vector 0. And we do a tail expansion in Harvard, a lot of dimensions here, right? I mean, in principle, we have nodes with degrees going all the way up. So we get our initial guy. Our first one is there's the first derivative here, and all of the first order terms, right? Theta 1t, theta 2, theta 3, 3. And then we have cross terms going out. There's plus other things there as well, right? So that's just one of them. Second derivative, but then we have the cross terms. So that's a nasty things out here. But this is, so from this we can look at this horrible thing and say, well, if this is non-zero, then there's some characters that are just infected for free, right? They don't need anyone else on. So this is always taking off. It self-excites. If it's equal to 0, it depends on this blob here, and it depends on the largest eigenvalue of this thing. Before we just said the slope is greater than 1. Right? We had this kind of story. There were more complications. There were deeper things. But the basic story was, well, here, if our g function was like this, and it takes off, right? And it was whether the slope is greater than 1. More deeply, this is an eigenvalue. And there's only 1, so it is also the largest eigenvalue. But if we have more things, we can choose, right? So it will take off if the largest eigenvalue is greater than 1. So we have a more complicated thing, but it's a very nice generalization. This is just to make our random network assortative. That's all. And it just explodes. Okay. Fun times here. So you can figure it out. It's not so bad. But this is it depends on this matrix, right? So this is JK, right? This is some horrible big matrix. And it'll depend on that. All right. Okay, so this is going to be the last thing, and then we get some fun. And when are we supposed to stop? 5:15. Yeah. Okay. It's all right. We can start on the next thing because I'll introduce this. Very nice. Okay, so here's just some results from a particular set of networks. They have a bit of a funny character to them, but they're a nice little toy model thing. You can look at it. It's a Newman paper here. Just a general thing here. So we have assortative, that's these guys. Neutral is in here, so no correlations, disassortative. So for this particular kind of spreading, and there are lots of different kinds of spreading we've talked about, but here's at least one result from this, which is that the assortative networks, as we increase the connectivity, they're more susceptible. Things take off in them. These ones are creating a barrier. The more disassortative it is, creates more of a barrier. But if things really spread in them, right, if it's connected enough, it's worse. So that's there's a bit of an interesting kind of transition at some point here. But this really depends on what's spreading. It really, if it's what we've called social threshold type things or biological, these things can be facilitated or hampered. You can imagine the social type ones get blocked more in the, you could imagine in the disassortative ones, right? Because there are lots, hubs are in the way all the time, right? So sort of, right? So you don't have many friends, but your friends have a lot of friends. So you can't influence them. They can influence you, but then you can't really spread it because all your friends have got lots of friends and they're like, I'm not going to listen to you, right? On the other hand, the assortative ones, and we've seen this with some simulations, so maybe you have kind of group structures, you can get some things to really take off in there, and it's a nice, awful sort of story where you have poorly connected nodes connected to other poorly connected nodes, and they're susceptible. So they create, you get a reservoir out of them, and then they can start to get ones that take 2 and 3 and more hits. So you can get these networks that on average look like nothing's going to happen in them. But because of sortativity, there's a vulnerability to them. So it's a dial, and it can really transform the way things behave. I could add a result. Yes?
I was just thinking about the nature of this sort of one and how it's essentially kind of functioning as a bipartite graph.
I mean, in the extreme version, you can make it like that. Yeah, right. And it's true. So, we have papers on this, actually, where you can dial it all the way up. And so we made a toy model, for instance, where there are 3s and 1s. So at one limit, the 3s are only connected to 1s. So each 3 has their 3 little friends, and they're all disconnected. It's all these little clusters. And then at the other limit, the 3s are only connected to 3s, and the 1s are connected, they're all paired off in little 1s. And the 3s are a nice, good, spready thing. So that, they're sort of, that allows it to happen there. But the other one, it tends to, it depends on the mechanism. Yeah. That was super fun to work on. Inspired by, but not applicable to reality. Yeah. Okay, let's have some more blowing things. Okay, cool. This bit you should not do. You shouldn't look at your Lego gun. Don't do that. This is pretty good, actually.
This is my water gun.
It's not hooked up to a hose, though, buddy. You gotta hook it up to.
It's pretty good.
Touche.
It's pretty good. Anyway, there are a few more of those. Oh, okay. Yeah, we'll go on. Good.
It's called the hyperdrive. Is he gonna do that? Boom!
Why do they put an ad in it? Of course it's getting millions of views. They put one in it. It's kind of 10-second thing. And destroy the Death Star. Right. Yeah. It's great. I don't know how long each one took. They're 10 seconds long. Anyway, high quality. All right. So that helps our psychology.
Educating this kid at such a young age about Star Wars.
Very important.
The video, it's a 4-year-old girl that's like telling the story of
No.
Star Wars.
Explaining it.
Yeah, it's like possibly the most adorable thing of all time. She's like got the whole story down with really good layout.
There's a couple of really good videos recently, and I think they're all opera singers. You know, I'm not going to show it, but it's the Disney princesses.
Oh yeah.
Have you seen that?
Yeah.
Yeah. Complaining about the whole, right. And they're trying to get Princess Leia in, that's another one, because she's part of the team now. They're trying to explain how it works. It's all filmed around Grant's tomb in New York. It's kind of funny. But the other one is about what is going, this is not a good plan. The stupid stories. But it's the one from Frozen. Very good. Yeah. Okay, I'm going to start you off on this. This is really nice madness. And we can go for another 10 years. No, minutes. Okay. All right. Of course, I thought we'd get through this, but no. Okay. All right, let's just lay out how this works. All right. So of course we've done these things. So we've had undirected. They've been undirected. We added assortativity, but they're still undirected. We thought about directions, but yeah, we talked about directions, but they weren't really directed. So we'll have directed ones. They're going to be unweighted. That's too hard. Weight is too hard. But we'll have a bit of okay, so this is the first thing. So now this is a tiny little guy. This is undirected. There's K incoming, K sub I incoming ones, K O outgoing ones, right? So every node could be like this. So this is going to be nice and easy to play with for contagion. It's built in. And so you have a joint degree distribution. So this is it's a natural thing to look at for the web and the way people contact each other and so on. You can have very different distributions versus out degree distributions. Very standard thing. So if we sum over both of those guys, we have to get 1. There are some, so there's going to be some sort of sneaky little things that what we're going to do is think about a more general one where we have undirected ones and directed edges mixed together. But first of all, this has to be true. So if we take our joint distribution, sum over K sub O, then we have to get the probability of getting a K sub I, right? That's be sitting there, and the opposite here, okay. And we have to have this balance. So for instance, if we sum over the distribution, right, we sum over both I and K sub I and K sub O, the in and out degrees, and we find the average in degree, right? This is what this is. We're finding the average in degree. That has to be equal to the average out degree because that thing has to match up. Simple thing, but that's good. So you can't just make up anything you want. And so they pretty quickly you get so we've talked about the giant component sort of business. Now we get, in principle, it depends on the network or your set of networks, or your family of networks. But you can have these kinds of things now. So we have a giant weakly connected component. So you take your network and take off the directions. So it's a giant component. Again, right? Giant component means that it's an infinite network and there's a macroscopic piece. You can see it from space. Okay. In the limit of the thing getting large. So there's that. That's so we'll call it weakly connected. There's a giant in component, a giant out component, a giant strongly connected component. So the web looks like this, for example. So the giant strongly connected component is this little character in here. So from every node, you can get to every other node on these directed links. The giant in component means that from any point in any node in here, you can get into this guy and then run around, but you can't get back out, right? And these ones are all reachable from here. Yeah? So you get stuck if you run down out here. You're like, oops. there are some tubes and some tendrils. You're allowed to have these little funny little pieces like this. So generally, this is a tree. All these trees coming out of here. Trees are good words, right? Branching tree things. But sometimes there might be some little loops floating around because they can be big.
In what way is a tube different than just being strongly connected, but really long pathways?
Well, so this could be a very big thing, and this can be a very big thing, and it just has a.
Just happenstance.
Yeah, I mean, it depends on the system how big this could be, but yeah. But it bypasses here, right? It's not getting into any of it. It's just, in principle, it could happen. Right. So you march along, and there's really so you can only really go on one directed path. Right. So if you go into here, you can run around everywhere, and then go out on a path. But this one, it's just structured so that you. Some disconnected ones. Okay. It depends. So, you line your family up. The typical thing we've done is say, let's take average degree, and we'll tune that, and we get a family of networks. Right? You can march through the network space in all sorts of ways. That's a natural way to do it. But you have to think about how your thing is made. Typically, so here's a general statement. You typically get this guy appearing first as you go through a more and more connected set or family, and then this team tends to appear around the same time as well. Right, phase transitions. Okay, so when you think about contagion, in terms of spreading, this thing is kind of like our critical mass story before. It depends on the thing, but right, stuff can get from everywhere to everywhere here, maybe. These are all triggering characters. They're outside of it. But they're not. This thing doesn't get lit up, and once it hits here, all of this blows as well. I mean, well, if it's a really bad, got the Ebola happening, then it goes all through here. But these, they're all, in the game, right? They're reachable. Okay, so that's it. So it's a different kind of structure, and you have to think about that. Okay, so let's. We'll just define these things, and we'll set them up. So the analyses are disjoint for these. They have different kinds of structures. We can put them all together. So this is a nice piece of work. Serrano and Bahuna and others came up with this plan. All right. So let's say each node has. We're not going to randomly wire up because this is not going to work, right? That's a bad thing to do. So the sort of idea before we would just randomly throw down links, we actually have to fix their local structure. And there have been more efforts to say, I want to fix the local structure so that this character has so many triangles around it. They're usually pretty dodgy kind of efforts. And then I'm going to sort of glue them together. I mean, one tries to think about how to do this, but it's hard. So these are all in vector links. These are out, and these are all undirected. So in principle, you have some, you just have some distribution over these three things. So we have a little vector for each node, KU, KI, KO, right? So it's a little column vector. So again, unweighted, but no, we're spreading things out. So, all right, easy to think about this, easy to think about this guy. Well, not easy, but I mean, we can do it, but we can actually treat it together and have these things fall back to the particular cases. Okay. So we need this sort of madness. You've got to have that, right? So we're going to sum over all the possible pieces. And so this is the in degree, the average in degree along the directed parts, and the average out degree. They just have to, so that was true before, it's still true. Otherwise it's, kind of loosey-goosey. The undirected ones, you can, mess around with them a lot more. These guys have to balance up. So you could retreat like this if you want, right? So just put in delta functions for these guys and a delta function for this guy, set it to a Kronecker delta function, turn them off. All right, so let's add correlations to this. So I just want to get through this definition of this madness, and then we will go about solving things on these models. Okay, correlations. Okay, so this is going to be a different approach. Before we had this matrix kind of thing. I mean, yeah. I mean, okay, it's fine. You'll see it's a similar kind of thing, but it's just the framing of it is different. All right, so this is probably an undirected edge. Starts at a node of, so it's this vectors, they're all vectors now too, right? A node that has this vector, k prime, goes to a node of vector k. So that's along an undirected edge. This is probably with an I superscript here, that it leaves a degree k prime node, arrives at a degree k node, and it comes in a sort of in the right way. It comes in along an indirected one. Right, so it's traveling on an indirected one. So it's doing this this thing here. And you have to define the other one, which is it's a connection thing. So you start at a k prime node. Let's say it's here, and you end up at a k node. You're just following some part of the network, and you went the wrong way. You kind of went the wrong way on a one-way street. So those things should, match up with each other. So now we have a more insane kind of balance. Before we just had that the average in degree has to be the average out degree. So you need some things. So this has to be related. So if we swap the degrees, they have to be related to each other. And these guys have to be connected as well. It's a bit different. Here we've flipped these guys. So they have to kind of connect to each other. That should be PI, sorry.
And by related, you don't mean equal, you just mean there's some.
Connected to, yeah. That should be a PI and that should be a PO. So let's see. So let's just do it and then you can run away. So, okay, so we're going to randomly choose an edge and we'll randomly choose an end and think about what happens. So let's say we get to the node that we chose is a degree k. And it's k prime at the other end. Okay, here's a bigger picture. Whoop. So this is the probability that, and it's undirected, right? Yeah, yep. So this has to be true. So this is just this is not a conditional probability, right? This is just the probability that each end is k prime, k. That should be fine. And then we can connect those guys through conditional probabilities, right? So the probability that one end is, the first end is k and the other end is k prime, should be the probability that at this one end we have, right, it's a probably k prime, there's a vector k prime thing, and this is the probability, this is the weighting that gives you the chance of hitting that guy on an undirected edge. Right, it has to be k sub u. That's the undirected part of it. And then given you start there, then you end up at a k prime node. And then the flip of this, right? So at one end you have the unprimed guy, just the plain k. This is the probability that you've reached it along a degree k sub u. Sorry, this is the probability you've reached along an undirected edge. And then this is the conditional probability that connects you back to the other guys. So these two have to match up. Which one?
See where the conditional one comes from.
This one?
Where does capital P of K prime and capital P of K prime?
Yeah, so they're just, you choose a node.
That's a probability of choosing that node.
Yep. Because that's underlying the whole thing as well, right?
Okay.
Yeah, yeah, exactly. Right. So these guys, think about these. So the first one, we pick a degree k node. We pick an edge, we go to one end, and we find that it's a degree k node, and that we're traveling along an outgoing edge, so that's good, and then against the direction of an incoming edge. That's possible too. Right, so we've jumped on this edge, we run along it one way, and we see that it's either an outgoing one, yep, An outgoing one is we bounce back from it, or it's actually an incoming one. A little mad. So you have to have this balance. So this is the same kind of thing. So you've picked out an edge. Probably that is just a directed edge that connects a k and a k prime independent of direction. You're just saying it's just all you're saying is you just relate to someone else. It's a directed edge. One end is a k, other end is a k prime. Has to have this connection, right? So it could have been that, you hit one, you're coming out on an outgoing node, and then given you started there, you run into, you travel into a degree k node along an incoming edge. So that's the connective part there. You're at the other end, and you travel along, and you come in the wrong way on an outgoing edge. So these things have to be connected. So it's a bit of a funny business. So if you want to, create these networks, these are the kind of balance pieces. We don't have to worry about them later on. I mean, in our calculations, we just have to make sure these were true. Yeah, so it's different to the previous slide because now you're starting at k prime, you're ending up at k. Stop the words. Okay, so that's the setup. It's a little nasty. Just to make sure those things are true, but in general, we have these distributions and we can start to think about spreading them. And so they have nice, interesting behavior, and will eventually emerge from contagion. But we have to go through this little joy as well. So, okay, so coolness. Yeah, good. I think you can be liberated.
Do you have class next Tuesday? No, right? Just next
You want class, what? You want it next Tuesday?
No, I was asking.
You know what? One thing we do is we could have another Tuesday because we've caught up, right? We're all balanced out. But we could have another Tuesday and then not have that very last Tuesday. We're supposed to have 3 more Thursdays and a Tuesday because the semester ends on a Wednesday. We could sneak another Tuesday in, and then you could not have to meet on that last week. You present them in the exam slot. I mean, we could move that, but but that's which is a Thursday, May 8th.
Some of us are flying to distant lands that evening.
Okay. Well, we can talk about that. Yeah. Right.
I could Skype. Yeah, I could Skype.
All right. Thank you, people.